Hello everybody, and thanks a lot to the organizers for giving me this opportunity to come here again. I was back here in 2008 for a nice conference organized by David and co-workers. It's always a pleasure to be back. And so I'll answer the questions that were raised by Lara and people in the audience, hopefully. I'm switching roles with Alex, and I'm giving, this is really an experimental talk in publishing, advertising some data that were obtained by a group in Pisa and Genoa, as I would say. So I'm going to talk about Coulomb drag, which was introduced by Alex in the first talk this morning. And I'm going to talk about drag anomalies that we have been observing consistently in hybrid structure that contain both graphene and gallium arsenide. So I'm taking a little bit of Alex talk, a little bit of Alan talk, making a linear combination in new heterostructures. And I must say it's not, we have not really done any serious microscopic theory on this, and I hope to collaborate here with Andrea and David on these issues. So I cannot really say that we understand really everything, but essentially the main result is the following. There is a plot here of the Coulomb drag resistance as a function of temperature, and instead of displaying usual Fermi-liquid behavior, where drag is a parametrically small effect in temperature that goes like t squared for small temperature, we see huge upturn of more than an order of magnitude that kick in at a temperature scale which is absolutely gigantic, which is of the order of 10 Kelvin. Okay, so this work was, as I said, done mainly by my experimental colleagues in Pisa that recently moved to Genoa, the Italian Institute of Technology, Vittorio Pellegrini and these collaborators, and Matteo has done a little bit of theory that I will talk about, and really the samples were optimized not really for transport, but from optics, for reasons that I will mention later in the talk, and come from the group of Andrea Ferrari in Cambridge, while gallium arsenide quantum well 2DECs come from Lauren Pfeiffer and Ken West. Okay, so Alex has already done a great job talking about drag. I'm going to say a couple of things more in my point of view on the graphene experiments. And so let me mention a few historical facts. So the first really idea came by this Russian physicist by the name of Pogrebnitsky, who is actually now a very, I've been told by Russian people, he's a very successful businessman, really making a lot of money. So, and so these people, Pogrebnitsky and Price, in the late 70s, came with coupling this idea of coupling two-dimensional systems in a rather non-conventional way through long-range Coulomb interactions. So the idea is of the basic setup is the following: you have two-dimensional electron systems which are separated by a distance d, and so there are two players. Okay, so the top layer and the bottom layer. So let me call the active layer the top one for the following reason. Okay, so I imagine to drive a current in the top layer just by applying the potential difference only to the top layer, and these two guys are electrically disconnected. They are completely separate from the point of view of electrical connections. Okay, so I'm going to talk. I'm going to refer to the bottom layer as the passive layer, and the reason is the following: is that precisely because of Coulomb interactions. Sorry. Yeah, sorry, I drive, yeah. So the bottom one is going to be the drive layer, as written here in the slides, and the top one is the passive. So current flow in the bottom layer, and due to electron-electron interactions, what happens is essentially that there is momentum which is imparted by electron-electron interactions during the Coulomb collisions on electrons in the top layer where current cannot flow. Okay, so this is the top layer is an open circuit, so the only thing that can happen is that a voltage drop builds up in the passive layer, which I'm calling here in this slide from Cambridge V drag. Okay, so this is a very well-known effect, has been studied by a variety of people from the theory point of view, and the first experiments were done are those mentioned by Alex, and also this work done by Gimaisen and co-workers back in the 90s. You can go through a phase-space argument or a microscopic, either Kubo formula or photon transport theory. You can build a parameter with dimensions of resistance, which is just the ratio of the voltage drop in the passive layer measured in units of the drive current in the active layer. This is a resistance, it's called in the literature drag resistance, and is a small effect that because of phase space Fermi statistics effects, you get a factor kBT roughly per layer cooperating to give you this weak effect. So drug resistance is vanishingly small with temperature. This was nicely shown by Jim Eisenstein and co-workers back in the 90s. As I said, and you see this Fermi liquid behavior. Okay, Coulomb drag is now used as a regular and standard routine probe of strong correlations in a variety of contexts. There are these nice experiments which are not yet understood when you drag a normal metal against a superconductor, then a Cordieu-Lafayette, which I don't think they are still yet explained. There is a lot of work that, as Alan was mentioning, that has been done in the quantum Hall regime. There is nice work done, dragging one-dimensional Luttinger liquids. In particular, there is a very recent science paper by the McGill group, and there is this work that Alan discussed extensively in the previous talk. And as Alex said, there has been a lot of work to try to search for exciton condensations in the absence of a magnetic field done in the semiconductor physics community, in particular by two groups, the Cambridge group and the Sandia group, with these two nice papers, exactly the same slide that Alex was showing, where Coulomb drag anomalies and in fact upturns and even violations of the Onzaga reciprocity relations that you would expect in the regime of linear response, which were observed back in 2000 or so. And so, as Alex said, one of the key points that these all gallium arsenide electron-hole double layers are extremely difficult to build, and only the patients of Cambridge people and the people of Sandia have essentially made it possible to do these experiments. So it's very difficult samples, really tremendously difficult. Okay. So, and as was mentioned several times, Coulomb drag has been really enjoying a revival. This slide has already been shown twice. This is a very influential paper in the field by Alan and co-workers, giving hope to the community to look for exciton condensation in zero magnetic field at very large temperatures. Okay, but there is a problem with graphene samples, in my opinion. The problem is sketched in this slide, as has been mentioned by several authors. Okay. So when you are at relatively high temperatures, as in this slide, you are at temperatures of the order of 80 Kelvin or so, you can measure your drag resistance as a function of system parameters. For example, this is as a function of carrier density in one of the two layers, and you fix temperature and distance in this case. These are experiments done at UT Austin by Tutuk and co-workers. These are not boron nitride fancy experiments. The spacer here is just aluminum oxide, so interlayer distances are much larger than the 1 nanometer that Alex was mentioning. And if you are at relatively large temperatures, there's no problem. You can do a many-body theory of it. As I said, it can be Kubo formula, or it can be Boltzmann transport theory in the Fermi liquid regime. And what you find is fantastic agreement between the theory, which is these curves, and the experimental data. The only parameter here is essentially the electric constant of the spacer, which is an atomically thin thing of the order, as I said, of 7 nanometers. So you have to measure that independently, and that's pretty much the only parameter. But as you go down in temperature, what you see is that the drag signal becomes a fluctuating quantity as a function of external parameters or system parameters. Like in this case, in these plots by Manuel, was fluctuating variable of the backgate voltages. There were classic experiments by Savchenko and co-workers in which it was fluctuating as a function of density, but in the graphene systems, these fluctuations show up really at a large temperature scale, in my opinion. So these experiments, very nice experiments by the Manchester group with a much fancier spacer, were discussed extensively by Alex, and will probably be mentioned definitely by Leonid later in the conference. And so the whole topic here about large fraction of the paper was devoted really to studying drag in a very non-Fermi liquid regime, in which the average carrier density in each of the two graphene layers is extremely small, and you have a very fancy behavior of the Coulomb drag that function system parameters like density and temperature. But you see that when you reach temperatures of the order of tens of Kelvin, like in this plot here, again, the drag signal becomes a fluctuating quantity of the system parameters. So, you know, just so probably it's fair to say that it would be difficult to achieve with linear bands exciton condensation. But in my opinion, low temperature physics, at least through this probe, which is drag, has not yet been probed because of precisely this problem of mesoscopic fluctuations. At least that's my point of view on the story. Okay. So just to summarize of the main ideas of this introduction, Coulomb drag is a routine tool now to study strong correlations between electrically isolated systems. All gallium arsenide, aluminum gallium arsenide samples have these problems in production, which are just difficult to produce, but extremely clean, nice samples, but are difficult to make, and measurements of Coulomb drag at very low temperatures, 1 Kelvin or so, in just van der Waals heterostructures, at least in this basic example of a graphene boron nitride. Heterostructures are hampered by mesoscopic fluctuations, as of my knowledge, which dates back to 2012 roughly. So I'm sure there's been progress in these 2 years or so. Okay. So back in 2012, we came up with just a little device that was, it's an hybrid device where you use the good things about both systems. Okay. So you use the fantastic quality of two-dimensional electron systems in gallium arsenide, and you can maybe perhaps imagine that there's going to be some interesting physics when you couple ordinary parabolic band Schrödinger fermions with the massless Dirac fermions in graphene. The real idea behind this proposal was that back in 2012 there were no many experiments probing optics, in particular plasmons, in graphene. These experiments were done by Basil and Toppens with scanning near-field spectroscopy techniques were not yet out there, so we were hoping to do standard inelastic light scattering on gallium arsenide and probing graphene plasmons through the Coulomb coupling between gallium arsenide and graphene. Gallium arsenide being a gap system, you can use these nice techniques of resonant inelastic light scattering. That was the idea. So the samples we had were, you know, later on built by a combination of so the Andrea Ferrari group and Lauren Pfeiffer were not optimized for transport, in the sense, unfortunately, we don't have gates as of today, top and bottom gates, to change separately the densities in these two-dimensional electron systems, and this will be an important problem later on. Okay? So you can go through the basic calculations. Again, as I said, Kubo formula in the linear response theory and Boltzmann transport. These are the two main diagrams which are believed to contribute to the drag resistivity, and to Larkin diagrams where the wavy lines are just some screened, dynamically screened effective interactions between electrons in different layers. And you can go really through the calculation very carefully and study drag as a function of parameters. And that's what we did, and I'll get back to how this theory compares with the data in just a second. Okay? So these are a little bit the samples, just to remind yourself. So we have graphene on top of a gallium arsenide quantum well, where a two-dimensional electron gas is hosted, and you can play the same games that I was mentioning at the beginning of the talk. I mean, you can switch the roles of passive versus active layer. So you can use graphene to measure the drag resistance as a function of drive current flowing in the 2-DAG, or you can reverse the roles and use instead graphene as a drive layer and measure the voltage drop in the two-dimensional electron gas. Again, the key thing here is have separate contacting to these two-dimensional electron systems. Okay? So nominally we have just parabolic band Schrödinger fermions in the two-dimensional electron gas and massless Dirac fermions in graphene. For reasons I really don't understand, seriously, I mean, once you do this transfer procedure from an exfoliated graphene sheet and you place it on top of gallium arsenide, for reasons I personally don't understand, it turns out that graphene is heavily hole-doped. Okay? So then you have a natural heterostructure in which, even without playing in this case with fancy top and bottom gates, you have a whole liquid which is placed 40 nanometers or 35 nanometers roughly away from an electron liquid, and you may hope to study this physics that Alex was mentioning also in these hybrid systems. Okay? So you have to be careful just patterning all bars in the two-dimensional electron system just to make sure that all the current which is flowing and the 2-DAG is also flowing graphene. There are a lot of technical difficulties, and it's not my job to describe them in this talk. Okay, so let's start from high temperature, and then let's look at the drag resistance as a function of temperature. In these two cases in which you have graphene playing the active or the passive role and vice versa. So these are these data with red and black circles as a function of temperature, and these traces here are our microscopic theoretical predictions based on Fermi liquid theory and Boltzmann transport as a function with no fitting parameter, as a function of just the interlayer distance, which in these experiments, depending on how thick is the well and according to different samples, you can actually put your numbers in, and this is the agreement. We don't know how to do better than this. Is definitely not as spectacular as the agreement for an all graphene heterostructure. Okay, so there is a problem here that you have already all noticed, and the problem is that there seems to be an apparent violation of Onzaga reciprocity. Which is quite large at temperatures above 40 Kelvin, and my experimental colleagues have carefully measured interlayer leakage currents, and they convinced themselves that this discrepancy can be to a large extent compensated by exactly taking into account the fact that at high temperatures the leakage, interlayer leakage between the two subsystems becomes rather large. Okay? So let me now focus instead on the low temperature physics and see what the experiment says. Okay, so these are experimental data for the drag resistance, this time measured in the two-dimensional electron gas. Okay, so we take the highest quality system, which in this particular case, for this particular sample, was the 2DAG in the gallium arsenide quantum well. We use it as a system where you really measure the voltage drop and therefore the drag resistance as a function of the drive current applied in the graphene sheet. And that's what you see. And why are we doing this? The reason is that when you do that when you do that below 10 Kelvin, 20 Kelvin or so, you cannot really measure the voltage. You cannot really measure drag in the graphene system, because the graphene system will display these mesoscopic fluctuations. So we use a dirty system, which in this case is graphene just drive, and we measure the drag resistance in the bottom system, which is a two-dimensional electron gas. So you see what happens as a function of temperature. So you start from the Fermi liquid. This is just a fit. It's not a microscopic theory. It's just a quadratic parabolic fit. And then when you go below a temperature scale, which is of the order of 5 Kelvin, there is a huge 1 order of magnitude increase in the drag signal as a function of temperature. The lowest temperature is 240 millikelvin. This data point there is maybe showing some saturation of the effect that we don't understand. It's there with its error bars, and this red curve is what I'm going to talk later in the talk. Okay, but these are the data without any manipulation. Okay. So precisely because, this was just one sample. In fact, it's two samples where we have single layer graphene on 2DAG that display precisely this enhancement and similar physics. We wanted to just try completely different sample, which was a bilayer graphene this time on gallium arsenide, and this is the closest experimental realization to this idea by Andrea, David, and Alex that Alex was talking about. Is let's increase perhaps the strength of electron-electron interactions by having more dispersive, less dispersive bands with a bilayer graphene in the AB stacked form that shows, as Alex already mentioned, these nice quadratic band touchings. They are, again, because of preparation reasons, you have holes in the graphene subsystem and in the 2DAG of electrons, and you have, again, an electron fluid at distances of the order of 30 nanometers. These are the raw data without any manipulation, just in the low temperature. In the low temperature phase, I'm not showing here the high temperature Fermi liquid regime, but this time the upturn scale is amazing. It's just 2 times larger than in the case of single layer graphene on gallium arsenide, and these are the data again down to 240 millikelvin, and they don't show any saturation whatsoever. And there is again a red trace I'm going to talk about in just a second. No sign of saturation again. And the upturn temperature scale is really gigantic. It's 10 Kelvin, again with more than 1 order of magnitude increase in the drag resistance, okay? And so this is, we were very happy with this, and we're talking also with David and Andrea, because points to this physics that, when you have perhaps, systems with, as well known in many other contexts, in electron gas physics with parabolic bands, you have an easier way to access strong correlations and therefore enhance the role of electron-electron interactions with respect to band kinetic energies, okay? So this is now my interpretation of the data, and it's a very optimistic one. I'm very open to discuss if you guys have other brilliant ideas. I don't have any brilliant idea. I'm telling you what I did when I saw this data first, okay? So it's a very optimistic point of view, so I'm sorry for that. And the optimistic point of view is that, in these, there have been several calculations, in particular a calculation by Ben Wu studying precisely the role of fluctuations above the mean field critical temperature for exciton condensation using a Kubo formula linear response theory. And we essentially have repeated, if you wish, these calculations, put them also nicely in the context of graphene more recently, but instead of using Kubo formula, we feel that it's much more transparent to set everything into a Boltzmann transport theory, whereas you know very well, the only careful and the only physical big ingredient which enters into the calculation is your scattering amplitude. The rest is just momentum and energy conservation, occupation factors, and velocities, nothing fancy. Okay, so if you want to capture exciton condensation, what you can do is do Gaussian fluctuations or simply sum up ladder diagrams in the electron-hole channel, and you just come up with an effective interaction that blows up when you hit the mean field critical temperature. That's all what we are doing, and there is a lot of people here in the audience which have huge expertise in this context. So nothing fancy. So you can plug this effective interaction into the Boltzmann transport calculation, and you end up with a drag resistance which has this behavior. And when you approach the singularity independent susceptibility at 0 center of mass momentum and conjugate energy, what happens is that this integral is strongly enhanced by pairing fluctuations, and the enhancement is logarithmic with this fashion. Okay, so what I then suggested my colleagues was just to do just a brute force fitting. Okay. We don't want to do any microscopic. We didn't have the time to do this very, very, very careful. Let's do just some, brute force fitting, and using this formula where there is a background here in the resistance, and then this logarithmic upturn as you approach the mean field, the critical temperature from above. You can try exponential functions. You can try power laws. You can put your data in log scale, in log scale. Nothing works as well, believe me, as a simple log. Okay, as I'm showing, it's not decades in temperature, I admit that, but there is no other fitting formula that works better than just a simple log formula. Okay, and so these are the data I'm showing you and our interpretation. So the interpretation is precisely what was pointed out by Lara in Alex's talk. And is the fact that what we believe we are observing is a large fluctuational region above a mean field critical temperature. If of course you understand that once the log kick in, because of the log form, you don't have predicting power on the value of Tc. Pretty much any Tc you choose below the lowest temperature you reach, which is below 240 millikelvin, will work. For example, this particular plot is with a Tc, a mean field Tc of 10 Kelvin. Here we are more constrained. We don't have any way of fitting this data with temperature which are less than 190 millikelvin, which is sorry, here I did a big mistake. I said 10 Kelvin. That was too optimistic. This was 10 millikelvin. This is 190 millikelvin. Okay. So this is the state of the art. I don't have anything more intelligent to say. Microscopic calculations, I've been waiting for a long time. I'd like to talk with David and Andrea about that. I didn't have really time to work on this past year. That's all I know, and I can definitely tell you that yes, that's great. And I definitely can tell you that there is some dirt under the rug, and I just want to discuss about the dirt under the rug now on this slide. Okay? So as I said, just for honesty, these samples were you know, the Cambridge group is well known to study optoelectronics, so we're not optimized for transport. So as of today, the guys in Pisa and Genoa tried very hard to put top and bottom gates to tune the density, in fact switch all the way from whole electron regime to whole to an electron regime, and hopefully kill this fluctuational regime once you go to just repulsive electron-electron interactions. That's something we would love to do. We are really struggling. They are really struggling to do these experiments and to place nice top gates on the sample, okay, on graphene in particular. Okay. One of the other problems is that, you know, since the densities come the way they come, it is what it is. So you look at the Fermi wave number in each layer. These are nice systems with spherical Fermi surfaces. You look at what is Kf in each of the two layers, and you find that there are large mismatches in the Fermi wave vector. So I mean, for the single layer sample is a mismatch in Kf of the order of 25%. For bilayer graphene on gallium arsenide is a mismatch of 30%. Okay, so referees, reviewers, nicely enough, and you know, they say, what the hell is happening? I mean, it's believed that superfluidity is easily killed by a large Fermi surface mismatch. And again, I mean, calculations are on the way. We hope to work more on this soon. But when you do calculations, which have been discussed by Alex, by including screening in the condensed phase, and going to the regime in which you are far away from the BCS limit, big weak coupling limit, where the critical temperatures are similar to these 10 millikelvin, 100 millikelvin temperature scales I was discussing above. There is a consensus, I think, in the literature, surely in the cold Darwin community, that superfluidity can resist large Fermi surface mismatches or large Fermi wave number mismatches. So that's our hope, but again, I don't have any microscopic theory to nail this down. A big issue, and Alex was always worried about this, is disorder. What is disorder doing? I mean, it's not graphene sheets made in Manchester, so the mobility of these samples is of the order of 2,000, and so it's not 20,000, 50,000 or so. So disorder, in particular carrier density, inhomogeneities maybe are playing a role, but you know, I don't have a theory there that can really explain this huge upturn just in terms of disorder, at least not the current theories which are available out there. And definitely one of the problems, it's a big thing that I would like to think about more carefully, is what's happening with Onzaga reciprocity, since all the region of fluctuational region in which you are measuring the upturn in the 2-DAG, if you do the reverse, graphene would show these mesoscopic fluctuations. So we are definitely in a regime where Onzaga reciprocity is broken, and we are not the only ones reporting Onzaga violations. Also, those early experiments that were mentioned by Alex, by the Cambridge group and the Sandia group, were showing upturns, although at temperature scales which were much, much lower, with an amplitude of the upturn that was much, much less, and that were also displaying Onzaga reciprocity. So probably you know, not everything is understood about a drug. In fact, even the Kubo formula approach that is typically used assumes linear response theory, so maybe it's a point, it's time to think about how to transcend that. Okay, so let me conclude by thanking you for your attention, and thanking also a lot of people we have been talking to about this upturn. It's really Rambert down in Utrecht, and next off, Fazio, and many other people here in the audience. And again, I'd like to thank David and Andrea for the invitation, and Alex for a lot of discussions when I was visiting Sydney. Thanks a lot.
So we are now open for questions.
Maybe I missed something, but it seems to me that the
Could you speak up again, please? Sorry.
Sorry. Okay.
Do you have a microphone?
It seems to me that the calculation that you have done here, including this calculation of the TC, tell you that whatever is the TC of the mean field TC of the system, you will see this log dependence above the mean field TC. So then you say, I don't want to compute what is the real TC. If I apply the formula and fit the data, then I would get a mean field TC of 10 Kelvin.
Yeah.
And that would be reasonable. So, well, in the sense that you try to do a calculation and estimate the mean field TC, and you got 300 Kelvin. So you say, I don't want to estimate the TC. I do a calculation. What are the fluctuations doing above whatever is the mean field TC? And then I get a log. So then what is the TC I fit from the experiment, and mean field is 10 Kelvin. What is the KT? We don't know, it will be below, but who cares?
Okay, so
That's
remember
correct.
that.
Just to
Yeah. So that's the logic. The only mistake in the logic is that the 300 or room temperature scales that they were talking about was for bilayer graphene on. Okay, so for these system parameters, including in particular the fact that the distance which has been used, which is in this experiment, is huge, right? And it's 10 times larger than the distance you would have in an atomically thin van der Waals heterostructure. It's you get down to these numbers, and according to these calculations that Andrea and David are doing, these are also reasonable numbers. So the logic is perfect. It's just there is no inconsistency between the fitted
But then the point is also that they were eventually pointing out the possibility to see BKT-like fluctuation between the mean field, which is room temperature, and the real TC. You are describing fluctuation above the mean field TC. So it's a completely different regime of fluctuation also, a different kind of fluctuation also. So eventually in bilayer system you should see different physics.
But this TC can be renormal. I mean, this approach, Boltzmann approach, you can do the same considering an effective TC which is renormalized. So this window of fluctuation. It can be phase fluctuation, but the fact that you have a very wide fluctuation region, we agree on this. Is 10 times the fluctuation region is 10 times the TC you are measuring.
But this is a mean field fluctuation region. It's not a BKT fluctuation region.
They are
You were
different.
saying that you have a big regime between mean field and KT, where fluctuation will not have a mean field character. If this is true. So like what people see in ordinary thin fields or whatever. Okay, no, just to make a connection between the two things. Okay.
One more question.
From general principles of the phase or the transitions, I would expect power law of the divergence.
Okay.
Logarithmic, it's something
You don't
very
like it?
extremely unusual.
Yeah,
Did you
Russians love it. Every Russian I talk to is like, wow,
that's
it's a
true.
lot. Again, very poor man's approach. I mean, you can put the data nicely, and all the fitting nicely with logs and sorry, with power laws, and the power laws really don't fit well, honestly. I can show you the data. It's private. I don't have the slides, but I can show you.
So you try power.
Oh yeah. So power law, absolutely. So exponential power law and the log. I started from the log because I was just very optimistic. But then we tried that, and really, the fitting procedure.
As Russians, we are more comfortable with power.
I think we can continue discussion during the coffee break.
Well,
Thanks to all the speakers.